Today I'm going to do tensor analysis and also introduce a little bit more about notation. And a little bit more about notation. So first, objectives. There are two. So the first objective, you guys need to be able to define and use tensors and tensor operators. So this is the first. And the second objective, so here define, usually you need to define using different notations. You need to use a for notation, use the for notation with the Einstein convention, summation convention, and also be able to use the matrix notation. And the second objective is to use the for notation, use the index notation. With Einstein summation convention. So these are the two objectives. Then for the contents, we went through vector analysis, so you guys know what are vectors and how to define vectors, how to do different types of operations with vectors. For example, the basic operations, we define the dot product, cross product, and also we talk about the changes in the vectors. So that is vector calculus. So we talk about different differential, nabla, symbol, Laplacian. So here, in order to get a good understanding of vector, so we do it in the same way. Start from what we are familiar with, that are vectors, to what we need to learn about. So that is tensors. So first, let's take a look at what a vector looks like. Again, this is a review. So for example, if we have U here, usually we say that in a general way is U, I, and EI. So this is the basic vector along the IX, UJ, EJ plus UK, EK. And sometimes we also use U1, E1. Possibly this is better because we're going to use I and J in a different way if we use the Einstein summation. So to avoid confusion, so let's do it in this way. So IJK just general things, and 1, 2, 3 there's more specific. And we use the Einstein convention. We know that we write it as UI, EI. If we have another one, V, we can sort VJ, EJ. So here we use 1, 2, 3 because we want to use J, for another vector. So to avoid confusion, so this is the full notation. This is full notation with summation convention, and let's use ijk in this way from now on. Use 1, 2, 3 this way for full notation to avoid confusion. So then, how to get from a vector to a tensor is actually is simpler than what you can think of. How to do it? How to construct a second-order tensor using two first-order tensors u and v. We know that a cross product of two vectors will give us a vector, right? So that's not a tensor. It's very simple. Actually, just put them together. Just put the two things together. You will get a second-order tensor. So we give it a name called juxtaposition. So that means put two things together. Juxtaposition of two vectors. So that will give us something called a dyadic. So it has a specific name. So dyadic is a name for second-order tensor. And if we put two u and v together, we're going to have something like this. U, v. So it's like u, I, e, I. v, j, e, j. So we need to use different subscripts for different vectors because we don't know the relationship between them. Actually, for something like this, one thing I can tell you is that you can do it in this way. This one equals ui vj, because ui vj, they're components of the vectors, so they're scalars. So we can move them around. So this is okay. And if you want to write the full notation, it's gonna be like this. Again, from now on for full notation we use 1, 2, 3. So u1, v1, then e1, we better use a different. I apologize. This is not. It's better because we don't know the relationship between. So here we assume if we use ij something like this, we assume that this. Let's see if we can do it in this way. Because if we use the full notation, we're gonna have some confusion because E1, EI, and EJ, they're not necessarily the same thing. Because if we use full notation, you're gonna have E1, E1. That means these two things are identical. So this is the problem. So let's do it in this way. So now, for u, let's say it's UIMI. This one is VJNJ. So that in this case, we don't assume that we have the same basis vectors. So they can be different. So in this case, we're going to have MI. So it's going to have M. Oh, sorry, then if it's 1, 2, then it's gonna be M1, N1. And plus, because here we used Einstein summation, so this is the summation, U1, V2, then it's going to be M1, N2. And keep going, U1, V3, we have M1, N3. So this is an index summation with Einstein convention, and the second row is the index is the full notation, and we can also write down the tensor here using using the matrix notation. So we can have U1 V1, U2 U1 V2, U1 V3, and U2 V1, U2 V2, U2 V3. So you can see that there's 3 components. And now we cannot call it 3 directions anymore because it's not like a vector. We have 3. If it's a vector, if it's a 1D array, 3 components, 3 directions. But now it's 2D. And each of them is a component or is an element. So it's an element of the matrix or component of this tensor. And this component that has a name, it's called a dyad. So each dyadic consists of 9 dyads. And here, these things and the juxtaposition of two basis vectors, they are the new basis for the vector. And if we want to take a look at what it looks like, look like this. For example, for M1 and 1, it's look like this. It's looked 1, 0, 0. So it's also, and if it's M1 and 2, so based on that understanding, we can understand the vector is 2D, this dyadic 2D vector in this way. This vector is a summation of 9 basis 2D vectors, right? This is 1, 2, 3, and this UIVI is a projection of the vector onto the first. You can think about this as one direction in a 1D vector. So this is a projection of UV on this one, M1 and 1. So here we get a 2D vector by putting 2 vectors together. However, general second order tensors are not necessarily formed by the juxtaposition of 2 vectors. So let's give out an example. So we can define a 2D vector directly. So we can can define a second order tensor directly as, for example, a second order tensor here. Again, I put a bar above it to tell that a second order tensor is Aij Mij. So Aij is the component or is the element in the matrix, and Mij, they are the basis vectors. And if we use matrix, we can write it in this way. And A11, A12, A13, A21, A22, A23. So this is how to define a vector used for index notation with Einstein convention, and also using a matrix notation. And if we are talking about tensor notation, just write it in this way. If you are talking about handwriting, you just write it in this way. Second, so let's move from the definition of tensors to the basic operation. We talk about a lot of basic operations for vectors, but for tensors, there's one extra operator that we need to know about. That is tensor products. Actually, I've already given out one example for tensor product. That is juxtaposition of two vectors. So if you want to get a very simple understanding of it, just think about it. Just put two vectors together. Of two vectors. So if you do that, actually, this is one type of tensor product. It's called a dyadic product. So this is a extension of vector analysis. So just UV, you will use a tensor notation. It's written like this. So this is a direct extension of vector analysis. This is what we did in the previous lectures. But we can put two tensors together, two tensors of any orders together. So in that case, it's not necessarily a dyadic product. It's a general tensor product. So actually, the tensor product has a few other names. So here I want to differentiate it, different names so that you guys don't be confused too much. In linear algebra, so dyadic product, if we deal with tensors of any orders, then we will get tensor product. But in linear algebra, we have something called outer product. And we usually use sign like U. We put a cross in a circle. V. Or sometimes use U, V, the transpose of V. We use something like this to represent the outer product. So outer product, many people believe that is, we can use it interchangeably with tensor product. So that means you can just put a U and a V together, or you can add this thing in between them to represent a tensor product. But the concept of outer product usually is discussed in the area of linear algebra. And tensor product is more abstract. So it's interchangeable. But this one is more abstract. And here you say that, oh, here we have an outer product. Do we have an inner product? So what is inner product? So that's a thing, that's a term. Then what is inner product? It's actually dot product or the scalar product. We know that cross product is also called vector product, and the dot product is also called scalar product. And dot product has another name called inner product. So it's sometimes very confusing. And outer product is tensor product, but the tensor product is more abstract. Let's not do a dyadic product anymore, because we know tensor product is a product of tensors of two any orders. So let's do it in this way. If we have A as Aij, Minj, and we have a U is a vector. So let's write this one as UK PK. You can see that it's really easy to run out of symbols. So that's why, to avoid confusion, we want to use 1, 2, 3 for notation. So if we do a outer product of second order tensor A and first order tensor or vector U, this one is also A, this U. We will get the following things: Aij, Minj, then nothing between them, or just put this sign. That is a circle with a cross, and then it's UK PK. So be careful, always use different subscripts, because we don't know the relationship between the components and the basis vectors. If you use the same thing, you assume there's a relationship between them. So let's avoid that. And we know that this A, capital letter Aij and UK, they are scalars, so they can be moved around. So this one equals Aij UK. And then we have Minj PK. This is a tensor product. And then we define a new operation. We know that whenever you define a new operation or new operator, we need to define rules for using that operator. So here, then let's talk about the rules for tensor product. So what rules do we usually discuss when we are talking about operators? CAD, right? Commutative, right? That means we can switch the position of two things that are next to each other. And second, the C, what is A? Yeah, associative. That means, when we have three terms, we can just put any two of them together. For distributive, is that, when we have the operation between one thing and the summation of two other things, we can associate the first thing and the other two things in the parentheses together. So that's distributive. Here, we also want to discuss things in this way. So first, CAD. So first, let's talk about C. C For commutative, we don't have commutative, so put a cross here. So that means for any product, any tensor product between two tensors A and B, so A and B, tensor product A and B does not equal the tensor product of B and A. So there's no commutativity. And then for the second one, A, associative. And this one, we have the following rules. So this one works. For example, we have A, B, C. And this one equals A, B, C, and equals A, B, C. And if we have scalars, this rule is also valid. For example, let's have alpha A, B. So actually, if it's a scalar, we can move the scalar around. So it could be something like alpha A, B, or A, alpha, B. So associativity does hold for the tensor product. Then last one, D, distributive. This one is also valid. So that means we have A, B, the tensor product of A and the summation of A and B and C. So this one equals AB plus AC. And in addition to the basic CAD, actually I want to mention one more thing. And you can see that here, we only talk about tensor product. How about adding the operators that we define in vector analysis? Dot product and the cross product, what's going to happen? So for that one, this set of rule is called dyadic algebra. And for this one, let's take a look. We have the following rules. First, for the dot product, we have C, A, B. And this one actually equals C, A, B. And we have A, B, C. This one also equals A. And this is for dot. If it's for cross product, if we have, for example, C cross product A, B, this is like C cross product A, then B. The same thing, if we have A, B cross product C, just like A, B, and C. So here we only have, all of them are vectors. However, this rule is also valid between tensors. So also because tensors can always be viewed as the combination of basic first order vectors, right? Just put them together. So we can use the rule in the same way. So after we get to know the outer product and the rules for outer product, for tensor product, we want to go back a little bit and to compare the outer product and one thing that we learned before, that's the inner product. So to get a better understanding of what's the difference and the relationship between what we are learning now and what we did before. So let's compare tensor So we know that is also outer product and dot inner. We know that this is also actually also scalar product, right? So it has three names. Actually, one easy way to compare these two things is to use the matrix notation. So if we use the matrix notation, the inner product look like this. U inner product, dot product V, or inner product, is going to be like U1, U2, and U3. And then V1, V2, and V3. We know that the inner product, the dot product between two vectors is a scalar, right? So we will get a scalar, which is like U1, V1 plus U2, V2 plus U3, V3. But for outer product, what it looks like. Could you guys make a guess? Scale with U and V. What's the outer product of U and V? Take a look at what we just did. For defining the defining a tensor at the very beginning by putting two vectors together. So what's the result of it? What it looks like. So it's going to be like, first transpose both of them. So U1, U2, and U3. And then V1, V2, and V3. Right? Yeah. So we will get something like U1, V1, U2, U1, V2, blah blah, 3 by 3. So this is the relationship between inner and outer product in a very simple way. It's a matrix notation because we know these two operators. And this is one way. Another way is that I want to introduce one more thing. That is, if we put these two things together, and we can notice that there's only one difference between them. So the difference, so what is the difference intuitively? What's the difference between this symbol and this set of symbols? The dot, right? That's the dot is the difference. So this is another way to understand it. The difference is this dot sign. And actually this dot sign has a meaning. And this thing is called a contraction. So you can see that the dot product or inner product can be understood as, first we have an outer product or tensor product, and then we have one additional thing. That is the contraction. So what the contraction does is that it does the following thing. So if we have Mi and J, so Mi and Nj are two sets of basic vectors. So you can think about two Cartesian coordinate systems. But they are at first, we put them together, that means we don't know the relationship between them. And then what the contraction does is that you say that these two are identical. So we are talking about the same coordinate system. So then it's the same. It will get something called this one, delta ij, and this one is actually a function of two variables, and it has a name. It's called Kronecker delta. And the Kronecker delta, the meaning of it is that it equals 1 if I equals j. It equals 0 if I does not equal j. So then, with this contraction thing, and also this Kronecker delta and one extra function, let's take a look at the definition of inner product again, dot product again, see what happens if with this new understanding. So for U and V, so at the very beginning is UI, MI, and VJ, NJ, right? And we know that we can write it as UI, VJ, MI, NJ. And for MI and J, this is a contraction. Sorry, there's a dotted line here. We cannot. If there's no dot, that means the outer product. But the difference here is a dot here. So between, I also missed the dot here. I apologize. There's a dot here. Oops. So there's a dot here. Just missed this one. Only has a dot. Two vectors will give us a delta. Two sets of basis vectors will give us a delta. Kronecker delta. So this one has another dot here. So this equals UI VJ delta IJ. Right? These two. This is a dot product between two vectors. Actually, here is two sets of basis vectors. And we know that they equals to delta IJ because this is the contraction. And the contraction means that IJ, they're identical. So we need to get this one. Can everybody understand this? So that's contraction. And then let's take a look at this one, see what happens. So this one, you rewrite down the full notation. Then it's UI, for example, let's use 1, 2, 3 for full notation. U1, V1, delta 1, 1 plus U1, V2, delta 1, 2 plus U1, V3, delta 1, 3 plus U1, U2, V1, delta 2, 1 plus U2, V2, delta 2, 2 plus U2, V3, delta 2, 3. And also there's 3 other terms. But you can take a look. So here, delta 1, 1, in this case, 1 equals 1, right? So it's 1. But for the second one, delta 1, 2, this should be 0, right? And keep going, this is also 0. So you will find that here, eventually we get U1, V1 plus U2, V2 plus U3, V3. So this is UI, VI. And you can understand this delta ij. If you have a delta ij, that means this I. What you can do is that, so this one equals U1, VJ, delta ij. So whenever you have something like this, so what you can do is that if you have this sign, what you can do is that you replace one with the other in the components. So get rid of it, but make all j equals I. So that's what happens. You can see that this is kind of a new understanding of what we did before. And since we introduced the Kronecker delta, I want to introduce another operator. It's called Levi-Civita. So here I want to introduce another symbol, Levi-Civita. And the Levi-Civita, we use this symbol, epsilon ijk. And this epsilon ijk is defined in this way. So it equals, there are three possibilities, 1, -1, and 0. So it equals 1 when the ijk, they has an order in the following way. For example, 1, 2, 3, 2, 3, 1, or 3, 1, 2. But if it's negative, it's gonna like, for example, 3, 2, 1, 1, 2, 3, 1, 3, 2, or 2, 1, 3. It's just like, you can understand in this way. For example, 1, 2, 3. So if it goes, a specific direction like this, it's 1. But if it's not a one direction, for example, it's not a 1, 2, 3. It's like 1, 3, 2. In this case, if it's clockwise, then it's 1. If it's counterclockwise, it's -1. If it's 0, 1. If it's 0, if I equals j equals k, or so it's 0 as long as any of the condition is satisfied. So the reason that we define this Levi-Civita is that because in the above we just use this Kronecker delta operation to simplify, the dot product. So here we want to use Levi-Civita to simplify another thing that we introduced before. That is the cross product. So for example, U cross product V. In the past, we said that the way that I show you guys is that this one equals the determinant of EI, EJ, EK, then UI, UJ, UK. Let's use 1, 2, 3, okay? So here to avoid confusion, because we are running out of symbols. So let's use 1, 2, 3, U1, U2, U3, and V1, V2, and V3. That's what we did before, right? Now I show you guys a new way. The new way is that a simple way to write down a cross product. It's very simple. It's like UI, VJ, epsilon IJK. And sorry, there's another thing here, EK. So this one, Levi-Civita, we can understand it as a scalar. So we can move these three things around. So this is a vector. So you can see that the dot product of two vectors will give us a vector. So I introduced this because we know that tensors, higher order tensors can be constructed with lower order tensors, right? As long as you know the operation between two first order tensors, two vectors, you will know how to deal with higher order tensors. So that's, and I want to give you guys simple ways for writing the things, the dot product and the cross product that we introduced before, because now if we use higher order tensors, now we can use these very simple ways to deal with them. So this is, and there's one more thing. So for 5, I want to introduce something that is more complicated. They call it double contraction. Actually, a dot, you can understand that it's a combination of a contraction and an outer product. So inner product is a combination of a dot, a contraction, and an outer product. Can everybody understand this? So now 2 dots, that means double contraction. But there are 2 ways for doing double contraction. There are 2 types of double contraction. So let's say we have sigma. We have sigma and tau. We have 2 second-order tensors. 2 ways of double contraction. One way is that sigma delta. And the other way is write the 2 dots in this way. So this will make a difference. So it's not very common in multiphysics, but you will possibly still see these 2 things in some occasions. So I do it in the following way. Let's still use E for all the basic vectors, but we use different subscripts to represent their different. It's okay if we do it in this way as long as we use the Einstein summation. So we have tau is use KL, E, K, E, L. So this will be equal to sigma ij and tau kl, because these 2 are vectors, so we can move them around. And this actually, if we write a double contraction in this way, it means, because we know that for tensor product, there's no commutatively, so we cannot change the position of 2, right? So here, we cannot change the position of EI and EJ. So let's say the first one, EI, let's call it the first one. Then it's the first one in the first tensor, and this is the second one in the first tensor. And this EK is the first one in the second tensor, and the EL is the second one in the second tensor. So if we write the double contraction this way, then we will have contraction between first one, and second one. So it's gonna be like this one. Because of that, we will get EI, EK, and EJ, and EL. And it is a contraction, so we will get sigma ij tau kl, then delta ik delta kl. So what's going to happen next? So how to get rid of these 2 delta Kronecker deltas? Oh, sorry, I apologize. Just JL, right? IK. So how to get rid of these 2 delta Kronecker deltas? If we remove them, what's going to happen? We need to assume we need to replace I with K or K with I, right? Because if I does not equal K, just 0. So then this just equals delta. Let's replace. Your 2 ways. You can replace I with K and K with I. It's the same thing. So let's replace k with I. So we're gonna have delta I j tau tau IL, right? And if then let's do it step by step, and then replace L with J. So it's gonna be delta IJ tau IJ. This delta IJRL, you want to remove it, you just need to replace J with L, subscript J with subscript L, or we will replace subscript L with J. So here we will replace L, this one, with J, and get rid of this. If you don't understand it, get it back to what we did here. Get it back to here. You can see that I spent some time here to explain what happened. So you can see that's how we get it from here to here. So that means because this one equals this one, so we can get one conclusion is that you want to get a delta ij, just assume that I equals j. Replace I with j, or replace j as one I. It does not matter. So for the other one, it's similar. So it's sigma ij ej, and then tau kl el. So it's different because this one will have like this. So two inner ones have a dot product, and the other two outer ones have another dot product. And because of that, you guys can write it down yourself. J tau kl. So we will have EI, the dot product between EI and EL. And the other one, EJ and EK. And do it in the same way to get rid of the two Kronecker deltas. We will get, oh, I apologize here. This is not delta, this is sigma. My bad, this is sigma. So we will get sigma ij tau ji. So this is two types of double contraction. So it's not a dot product anymore, but we can understand it as a combination of two dot products. And then I want to keep moving on. Let's do the second part. Let's do the notation thing. Actually, I've already introduced some basics about notation, but here I want to offer some actual information. So we covered, I think it's three types of notations. Roughly there are two types. One is tensor notation, one is index notation. But for index notations, we did two. So two types of notation. Tensor notation. So for tensor notation, we just write down things, in different ways, and also use different symbols for different operations between different tensors. It's very simple, it's very concise, but you need to remember the meaning of each term, and also remember the meaning of the operation between any two terms. So you know the meaning, then you can write it in this way. And we will use this tensor notation a lot in later chapters for monolithic physics and for multiphysics. But at the very beginning, when we are doing mathematics, we mostly use the index notation, because now you guys still don't understand the meaning of, for example, dot product. What does a dot product mean? What's the operation we will have between different components? Now you don't have a clear idea. Now we want to use index notation. So for this one, it's very concise, but you need to know need to know the meaning of symbols. Symbols means both, the variables and also the operators. And operators. But the other one is index notation. And for index notation, in factor 2, so 1 is the comprehensive one. That you write down each term. The other one, you use the Einstein convention. So this thing is easy to understand. And actually another advantage of using index notation is that it's very easy to use it to derive for deductions. For example, if you want to derive your own Gauss equation, you want to derive something constitutive relationships, it's very convenient to use the index notation. So it's easy to understand. And it's good for deductions. So you need to know both. And first, so in order to get a better understanding of this notation, let's do it in the following way. Let's first, so we will be focusing on in index notation. Now from now on, we will be focusing on this one. For the comprehensive, this one is you usually do it at the very beginning, when you don't have understanding of the terms and the basis factors. Now you got a better understanding, so we will start with the index notation with Einstein convention. So for this one, let's first talk about rules. So this is the rule again. It's for index notation with the Einstein convention. And for the rules, we have several rules. So the first rule is that a index never appears more than 2 times. So for example, if we have something like Aij, Bjk, Cnk, so this is good. But if we have something like Aij, Bik, Cik, I appears 3 times. So this one violates the rule. So this one does not have a meaning in the index notation with the Einstein convention. And if appears once, this index calls a free index. And if it appears twice, this index is called a dummy index. And what does what does a dummy index imply? Appears twice, according to the Einstein convention. So what is the Einstein convention again? Whenever we have a subscript or index that appears twice, that means summation, right? You need to add things up. So keep this in mind. There are two possibilities: appear once, appear twice. Appear once, that means free index. That means if a free index, that is, you need to go over all the possibilities. For example, if you have a free index of I, if in a 3D space, you need to go through A1, 2, 3. But if it's a summation, if it appears twice, that means we need to do a summation. So this is the first rule. Second rule, free indices on each term of the equation must agree. For example, if we want to write down that C, a vector C equals a vector A plus B, then because here we have a vector, so we should have one index or one subscript, right? So this, if we use the index notation with the Einstein summation, here it's just like Ci equals Ai plus Bi. This one is good. And we can never have something like Ai plus Bj. This one does not work, does not mean anything in this convention. And give you another example. For example, if we say A equals a vector A equals A B and X. This one, actually, if you want to use it, write it using index notation with Einstein convention, it's just like AI equals AIJ BJK and XI. Oh, wait a second. This should be, apologize, should be AK. The reason is that here you can see that we have two terms in this equation. One term is on the left hand side of this equal sign. The other one is on the right side. So you can see that on the right side we have, is I a free index or a dummy index? Dummy, right? Because we have it appears twice. And what about J? Dummy or free? Dummy. So these two means summation, right? And there's only one free index K. On the left, we also have a K. So it's valid according to this rule. And I can give out two bad examples which, that violate this rule. For example, if I write Xi equals Aij, this one is wrong. First, they represent two tensors of different orders. This is the first order, they only have one index, the other one has two. So And also, one has one free index, the other one have two free indices. So wrong. The other one, xi equals ajk uk. Is this one valid? K appeared twice. This is valid according to the first rule, right? And then we have one free index j here, and the other one we have the free index is I. So free index I and free index j, they do not agree with each other. So here this must agree, right? So it's invalid. And this is the second rule. Third rule. So free and dummy indices can be changed to other symbols without altering the meaning of an expression. So free and dummy indices can be changed to other symbols. But you need to do it. We want to make sure one thing. If you want to change the free index, for example, if we want to change free index from I to j for one equation, you want to make sure that you change all the I to j. So that's the thing that you need to make sure. And if you change the dummy index, for example, j to another symbol, k, you want to make sure that you replace every j with k. So for example, the following thing, xi equals aij xj. This one, we can replace, for example, free index. What's the free index in this equation? I or j? Which one is free? I, right? So let's say we want to replace I, the free index I, with another k. xk equals akj xj. So these two equations, they're identical. They're the same thing. We just change the symbol. Or we can also change the dummy index. Let's say sk equals akj. Let's change the k to l, okay? So KL XL is also valid. And also, the free indices, they agree.
I think I'm falling for you.